시작하면 되나 그냥?
네, 지금 시작하셔야 돼요.
몇 명이나 들었어요?
줌에는 15명이고요.
유튜브 채널에
시작했습니다.
시작했고요. 네. 네, 안녕하세요. 제 소리가 잘 들리는지 모르겠습니다. 제가 뭐 사운드 테스트 몇 개 나왔고요. 오늘은
Could we start with English before so that he knows?
Oh,
Yeah.
I'm okay.
Yeah, I'll introduce in Korean and then I'll just switch to English.
Yep, I'm good.
Let's you start. 예, 안녕하세요. 저희 그 퀀텀 센터 Q 센터죠. 양정보 연구지원 센터에서 진행하는 특별 세미나 오늘 시작했습니다. 오늘은 IBM에서 양자 쪽 총괄하고 계시는 제이 감베타 박사님을 모시고 듣기로 하셨어요. 제이 감베타 박사님은 또 그리피스 대학에서 박사학위 하시고 미국 물리학회 펠로우시고요. 그다음에 IBM 펠로우십니다. 그래서 사실상 지난 10몇 년간 지나온 IBM 그 양자 컴퓨터 일을 앞에서 최전선에서 이끌고 계시는 분이고 상당히 많은 업적을 내신 분이에요. 그래서 오늘은 상당히 일반적인 강의를 해주시긴 하겠지만 여러분들한테 좋은 인사이트를 주실 거라고 생각합니다. Let me introduce Dr. J. Gambetta, who is from IBM, and he is actually IBM fellow, who has been leading the quantum computer technology of IBM for last 10 plus years. So we expect really introductory talk today, but I hope he will give a really great insight to our students and audiences. And many audiences are here on site. Also, they are coming to the Zoom link and also YouTube videos. So, if you have questions, you can just place the questions in the chat window, etc. I don't know we can cover all the questions, but some of the questions we try to cover it. Okay, Jay, please.
Thank you very much, Professor Jong. I'm happy to be here. It's the first time I've made it out to SKQU. I know that many people here have been working with IBM Quantum for a while, and so I'm very proud to be out here and to talk to you. I'm going to just give an overview of how I see quantum, how we are doing things, how the different things we're building, and I'll be happy to go into any area from IBM Quantum that you have questions on. So why do I care about quantum computing? Well, we all hope that eventually we'll solve problems that matter in a big way for society, whether it's understanding nature better, like say better understanding of condensed matter physics or high-energy physics, or improving machine learning. These are big goals. I'm not going to say today quantum computing can touch any of these, but it is possible that quantum computing may have a little bit of influence in all these areas, and I'll try and give you my intuition for this. But these set up some really large areas that are worthwhile to investigate because they can have a huge impact on us as a society. So reading from the top, just having better efficient catalysts, more efficient chemistry to process, improving materials, material science, better materials, understanding physics where quantum mechanics really dominates, improving machine learning in areas where machine learning is hard to work on some type of data, understanding better optimization and risks, and maybe even in the future understanding better antibiotics than things associated with health. Before I go there, I wanted to go a step back. One of the most famous algorithms I would ever say was the Phosphorus Transform. This was an algorithm that took a signal that was, say, hard for us to understand, and if you do a Phosphorus Transform of it, it becomes really easy for us to tell what's going on. This is like a representation. It's looking at data in a different way. And by looking at data in a different way, we can reveal something in it. So I like to think of the most powerful thing that we've seen in classical compute is representations. You can go even further. Whole businesses, especially important to IBM, are built on the representation of databases. We can even go further and say, well, we have spectral representation like the Fourier transform, relational representation. Artificial intelligence is emerging, well, has emerged as one of another type of representations of understanding how things are going on. Graph representations, all the things that go into, say, looking for connections, networks, social media, all of these, how we better bring ads to us. All of these are related to looking at data in a different way. So the way I think of quantum computing is the quantum circuit is a new representation. It's a new representation of math, a math that was particularly hard for us to do allows us to look at something that we couldn't have looked at before in a classical way. And so this representation, why we care about it, is it turns out that the quantum circuit can have an easy mapping to a lot of problems in, say, nature, physics, chemistry, material science. Also, the quantum circuit has representations for data that has some type of structure. Most famous that you probably have all heard of is the factoring algorithm. This turns out to be an algorithm where I encode data into using a modulo function, and then I do a Phosphorus Transform of that data, and I can reveal something about what's going on. Other types of structure that could be important, well, will be very important, is other quantum circuits for ranking, other quantum circuits for machine learning. We put a lot of effort into the machine learning, and I'd happily go into some questions on that. Then there are circuits that are just associated with just generic polynomial speedups. Usually, these are use a technique that in quantum we call amplitude estimation. But what these give you is a way that you could look at optimization problems of Monte Carlo. So the only thing that I want you to take away from this is that you can think of the quantum circuit as this new representation. And with this new representation, can we learn something more about the data? And if you take that to a next step, what we're seeing is a lot of our partners are interested in this because take those fundamental physics things and you start to say, well, can I design better batteries? Can I come up with better catalysts? Can I look for classification that works where typical classical algorithms fail? Can I look at things such as fraud detection? Can I look at vehicle routing? Can I look at flight route optimization? All of these things can be related back to the algorithms that we're investigating in the quantum for these different areas. And each one of these, I think it's easy to imagine how we can see it would have a big impact on society. We're already seeing, definitely with a lot of industries, that they're already interested. Amgen, which is a famous company in America for health, is looking at machine learning to look at large data. Boeing makes airplanes. They're interested in understanding, can I make lighter wings? Can I see if optimization can help in that? Exxon are improving the accuracy for understanding energy scales and seeing if this can help them in understanding how to predict chemical reactions. Woodside, which happens to be an Australian company, is looking at, can I use machine learning to look for structure and understand signals when I'm looking for periodic signals and understanding rocks in the ground. All of these are actually industries getting interested to ask the question, is quantum computing going to impact them? So what is quantum computing? To me, the way I look at it is, it's the first time in history the field of computing has ever branched. So when we go forward and we look back, we will say, before there was something that we call classical and quantum. So we've seen great advances in the transistors. Obviously, from the mechanical to the nanosheet work that is the nanosheet of hitting 2 nanometers that IBM recently did, also working and the collaborations that IBM has with Samsung and things, and pushing the limit of what a transistor is. But the important part that I want to get across is this will keep going. Classical computing will keep going. But we're actually at a point where a new field is branching, and that is quantum computing. It computes with this circuit in a completely different way. So in 2016, we decided to put a quantum computer on the cloud. The main reason I decided to do this is I would talk to a lot of my colleagues, and they would ask me, can you try and do this paper? Can you try and investigate this? And so I said, well, why can't I just take one of our systems, put it on the cloud, and let people do their own investigation? Since then, in the early days, I think in the first week we had 1,000 people sign up, and now we have over 300,000 users running close to 4 billion circuits. So those circuits I talked about, we get about 4 billion circuits a day run on the machines. And the total papers published with this is around 800 and growing. So what this suggests is we definitely have created a tool for doing science. At the heart, the IBM Quantum System One is our fundamental quantum computer that powers all of our systems. It's a system that obviously has a quantum processor inside it. It's also got electronics that defines custom-built electronics for controlling it. It's built in a nice glass container, which one looks good, but it's also used there to control the temperature, so it can stay very stable and reliable. And this has been the core to all of the systems that we have today. And in fact, we have 24 quantum systems that are available for people to use, ranging from Washington, which is a 127 qubit machine that we just made available recently, all the way down to a 1 qubit machine that we call IBM that allows you to explore pulse and sort of physics on that way. And so there are multiple of these systems, and I'll go a bit more into them as I go. So as I said, there's 3.5 billion circuits running each day, but more importantly, the growth of the number of uses of these systems is exponential. It looks like every day there's more and more, exponentially more circuits getting run on these machines. So this definitely suggests that there will be an industry, in my view, that is created where there will be over 1 trillion circuits a day running. And so I actually think of everything that we're trying to do is how do we keep driving the amount of actual circuits that can be done, and so that people can use them for exploring the different type of research. The same is also true for the papers. We see the papers growing every year more and more. The dark blue are published, the light blue are preprint papers. And we see the learners. I think we have 3 million people we've touched with quantum computing. That includes blogs, hackathons, all the different type tweets, Medium, all the things that we do that go out to the community. And we see an industry that has grown quite large. There's over 170 industry and national partners of our Q network. Obviously, SKKU is one of the hub members. With over 35, I just showed 4 at the start, different research projects that are getting done with different industries. So I see this quantum computing becoming a research tool. What do I mean by that? I mean that it's actually getting useful for people to do something with it, whether it's prove that something's quantum mechanically. One of the biggest challenges that I think we have in quantum computing is as we make our systems bigger and bigger, how do we prove that they're quantum mechanical? How do we prove that they're going to continue to obey the laws of quantum mechanics? We just take that for assumption. But actually proving that they still stay quantum mechanical turns out to be a really, really hard challenge. Because if you could simulate it and predict what it should do, then there would be no point in the first place of actually making a quantum computer. So coming up with different type of metrics and measurements to prove that the system is quantum mechanical, I think is a huge fundamental research question. Answering just what does it mean to be a quantum computer. We also see in the last APS many different papers. So the American Physical Sciences, a large physics conference, are published using this for different types of research. So this definitely says it's becoming a tool. The second is, and I'm really excited about this area, is I would love quantum mechanics to be useful for condensed matter physics. How do we actually build a machine that can influence us understanding problems that we've had a long time, difficult time trying to explain? We cannot predict the solutions of many of these spin systems or more exotic condensed matter, the most famous obviously being high TC. But can we start to actually model some of these spin systems with quantum computers? Of course, today, we can't do anything we can't predict, but we're seeing more and more scientists start to explore different types of exotic models. either from simulating the 1D icing model with the transverse field, Heisenberg model, to the time crystals, which is a certain type of symmetry. So I actually think these are suggesting that there is starting to emerge as a tool for looking at condensed matter. Then you can go to a completely different area of physics, high energy physics. It turns out that it gets so much data it's hard to classify. Can we use machine learning, quantum machine learning, to better classify the data that the CERN detector is detecting? In collaboration with CERN, that's actually one of the questions that the team looked at. And they found that with the quantum machine learning, whilst it was still a restricted model, was actually performing quite well at predicting the data that was measured there. Second is understanding more exotic lattice gauges and modeling it with trotterization. Can you model and predict other types of collisions for particle physics? These are other questions that are emerging. So I hope I've convinced you that as you grow this community, this is moving from a system to a tool for science. The philosophy that I try to drive at IBM Quantum is we do not want to make our tools, our quantum computers, we don't have any internally that are better than the ones that we provide to the community. So we have this philosophy that we have two types of systems. We call the bottom ones core systems. These systems we've vetted, measured, and looked at them for so long that we're confident they'll stay up. We're confident they'll always be ready, that any user can use them. To get core qualified, you have to know all the types of collisions, all the types of things that can go wrong. And so we put a lot of effort into what we call core systems. But because we don't want to delay how fast we get systems, we also have a different category of systems. And I invite you all to check them out when you go through the hub. We call these exploratory systems. As soon as we have an idea, like a new type of readout, a larger number of qubits, we put that straight actually online, and it becomes a system for us to test. In fact, we take it so serious that most of the research papers that we've done with these systems, whether it's, and I'll talk a little bit about some of them, understanding error mitigation, looking at machine learning, or measuring quantum volume, are all done with machines that we make available to the community of users. And that's a philosophy choice. Like, we've chosen that to make sure that we grow this ecosystem, I don't want any of the IBM Quantum devices to be extra devices behind a glass wall. So as soon as we have a new idea, make a new system, we put it out there and we make it available. At the same time, making sure we have high rigor in what we call core systems, because if we're providing systems with high reliability, you need to be sure that it's going to work. And so this allows us to have this both model of providing a stable system, but also bringing new features as quick as possible. This is often not appreciated. I like to call it agile hardware development, but this is how we model our hardware and how we work and deliver our hardware. So we work on superconducting qubits. I'm assuming most people know superconducting qubits. I'm not going to go too much into the details. It just gives you some high-level intuition why I like them. I've been obviously doing quantum computing now for, I forget, over 20 years, a few years. But superconducting qubits, there's three things that kind of matter. You have to be able to have strong interactions so you can do gates and read out fast. You have to have high coherence. You have to be able to isolate it from its environment. So you have to be able to engineer away degrees of freedom and come up with methods that can clean it to allow it to have high coherence. And third, you have to be able to scale it up, go to bigger and bigger systems. Qubits tends to be the optimal over all three of them. They're scalable because we can leverage both the CMOS technology that has driven the digital industry for the last, 50 years, but also microwave technology. We can leverage the ability that we've made precise microwave signals, which are used in radar detection and many of these different things. So by using both the combination of microwave technology and existing CMOS, we're able to scale these. Because we can put them wherever we want and drive high interactions, we can get high capacity. And because we can keep pushing the limits of coherence, this one turns out to be one of the hardest, we can keep making them better and better. So when you think of a processor, those three things come and matter. So the first one being the scale, how big the system can be. When we say 127 qubits and we talk about the different number of qubits that we're actually making, those numbers are not so important. What is actually more important is the fundamental technology that went behind them to allow each of them to go. For instance, to get a 27 qubit system to work, due to the natural variations in the fabrication, the collision, we call them collisions, but the device would just be inoperable. We had to develop a technique where we could use a laser to go in there, shoot the qubits, and adjust their frequencies so we could get high yield. To go to 65 qubits, it was actually limited not by the size of the chip, but by all the componentry around it, all the amplifiers, all the isolators, and all this. So you had to develop a multiplex technology that meant you could read out multiple qubits through the one readout channel. So a single amplifier could read out, in case in the 65, I believe it was 8 to 1, and we can get up to 10 to 1 now. To go to the Eagle, and why we're most really excited by this technology is, and I'll say a bit more of it later, is we had to basically get multi-level wiring and through substrate vias to make sure that we could actually get packaging that would allow us to scale all the way up to Condor and above. At Osprey, it's actually limited, so 433 qubits, by the number of wires that go into the machine. So you have to change from coax wires to what we call flex. At 1,000, you start to be limited by what we call the space transformer. But putting all this together, in November last year, we released Eagle. As you saw at the start, it's available as IBM Washington. It has coherence that is comparable to the 27. But the main thing that is the most important thing about the Eagle is it was these, I'll go back and show you. But so here's the qubit, and you see the qubit is coupled to a pad that'll be the through substrate via. But if you look in this video, it's multiple levels of stacks. So it's the first time that what we've actually done is created a chip that is multiple levels. And so now I can have the qubits on one level, I can have the readout lines on another level, and I can have all the input, and it's like a highway of bridges. I can go over and under, so I can connect anywhere I want and be able to connect to the qubits. We did all of this while keeping the coherence, and that type of packaging is why we're confident that we'll get up to the 1,000 qubit or so going forward. So quality. This is related to coherence. Think of this as how good is the machine obeying quantum mechanics? And I know I said at the start this is a hard thing to do, but for small enough systems, we can actually measure and predict it. So there's fundamentals associated with coherence. So in our standard 27, we get about 100 milliseconds. With our new processor, which is a Falcon R8, so it's a 27 qubit, it's a completely new processor. We got about a 3 times improvement of coherence. With our test devices that are underway, these are just single qubit tests, we're actually getting up almost to a millisecond. So I expect this year we'll be integrating these higher coherences and getting almost a factor of 10 improvement in the coherence in our larger devices. So you can kind of see that we've made 100, which I said the Eagle is about. We've got about a factor of 3 with the improved new processor, and we'll probably get another factor of 3 as we integrate the second new processor into it. Along with coherence is also the quality, the gate error. We continually see every iteration with the new coherences and the new features that are built in, the best error for the system continues to go down, with us now getting around 3 nines fidelity. So this definitely shows a process of getting to a small enough error rate that we believe we can do things like error correction and beyond. Also, to push the quality, and this shows how much software and quantum and hardware are coupled, is the way you compile it to the hardware is not independent of the actual hardware. Depending on which gates work better, depending on the connectivity, you can make drastic differences in the compiler, and why this is, I think, is one of the most open and important challenges that needs to be solved. And of course, getting low noise, cost-effective electronics. All of this, we set our goal that we double what we call the quantum volume each year, and we're working to the next iteration on this. Sorry. Talking with a mask is a little bit difficult. So the third is speed. And what matters in speed is a user wants to run something. So how fast can a result be returned to a user? That's going to depend on some core things, like how fast the gates are, how fast the readout is. And in fact, going from R4 Falcon to R5 Falcon, we improved the readout from 5 microseconds to 300 nanoseconds by integrating new technology that allowed you to keep high coherence but have a large readout cavity. But we put all this together to define a new quantity that we call flops, which you can think of as the quantum analogy of flops from classical. How many of those circuit layer operations you can do per second. And so our goal is to keep pushing the limit of this. If we look at our technology, we get about 2,000 clops. We probably can get another, we're about 2% efficient. So there's a lot more efficiency still to be derived into the software. But this I think we can probably get up to about 200,000 or something like that. But that's going to set how fast can those circuits go. If you compare it to other technologies, they would be in my view, in a couple of hundred. So why does this matter? Well, if I actually want to do something like chemistry, I want to map out a chemistry molecule, I actually have to run 5 billion quantum circuits. So if I need to run that many quantum circuits, and it takes me, say, I don't know, what would be a good example? It takes me a month on one architecture. If I'm 10,000 slower, you can imagine it'll be years on another. So if I need to run that many circuits, we need those circuits to be run as fast as possible that we could. And I'll go through a little bit of an example of how you do this problem so you can sort of see. So usually you would take one of these problems, and you can see where I'm going and how I see quantum computing changing to allow us to do more. So the first step is usually you take this problem, say some molecule, you'll map it to some type of qubits. This mapping will actually make both parameterized circuits. So you'll make something that will run on a quantum computer, and it also makes some classical calculations that would run on, say, a classical computer. Next, as I said, you would take this problem instance and map it to the quantum circuits, and it may be billions of them. Then you would take those billions of quantum circuits, and you'd run it on hardware, and you get returned a lot of data, a lot of zeros and ones. One of the problems we have at the moment is this is currently how you use the quantum computer, and getting a lot of zeros and ones are not very good for domain people or physicists to really convert and to go to the next step. And so what we're starting to see is we've got to develop techniques that post-process classical methods that take these zeros and ones and turn them into doubles or some type of list of numbers. And you can imagine that you may even do further classical calculation of, say, extrapolation or other methods that take these numbers and turn it into a single number. So all of this says that there are different things that are needed for us to make it easier to run a quantum computer. You need to get better ideas of how you do that mapping. You need to have, as I said, high-performance compiler I would argue this is one of the most important problems that I would love to see people working on. You need to optimize the classical quantum communication if I'm going to run billions of these circuits. This one I'll talk a little bit about, but it's important to me. You need to go to a structure that is event-driven. What I mean by that is I go send something off to a classical computer. I go something off to a quantum computer. My architecture is in a way that when I send them off, I can wait until they come back and not be, I can start, like I send one off to one, and I can send the other one off to the other, and I don't have to wait until one finishes before I send the second one off. So I get some type of parallelization built in. And so you go towards an architecture that is very event-driven. Obviously, you need better quantum hardware that gets larger and larger. And you need better ways of doing the error mitigation and ultimately error correction. This is a lot. And so the only way that we can make this effective and to really drive quantum computing faster is we need to build the software architecture in a way that the community, you guys, can just focus on your code, not having to worry about how I manage, say, the events or the hardware, but how my code is going to work. And you don't have to be driven too much by working out, do I need containers technology, or do I need some type of classical library? And so when you put all this together, it starts to drive an architecture that I'll talk about next. And I just wanted to throw this quote up because I really like this quote. It reminds me of how I've approached science my whole life. If you've got a problem and you want to solve it, we should spend more time thinking about the problem and less time actually solving it, because thinking about it and structuring this whole architecture together is the most important part, and that takes all the work. So what is the architecture that we're going towards? This is Qiskit runtime. We released it just last year. I'm not sure that many of you have had a chance of trying it. It came out maybe November, October last year. But it's moving from sending a circuit to sending a program. And now once you've got a program, you basically have a simple API that can take what you want to do, say developed in Qiskit, you extract a program. That program will generate the quantum circuits locally close to a hardware, generate, say, the pulses that go on the hardware, bring it back, and continue this loop in a really fast time. And as an example, what we've seen already for that chemistry problem that I said of mapping out, say, the bonding of lithium hydrogen, the old traditional way of sending individual circuits compared to the new way is about 4 times faster, and a combination of all the different improvements in the hardware leads to this whole way of investigating chemistry to be over 120 times faster. And so you can see this is moving from circuits to a program. And in fact, you can start to ask, what are the primitive programs for quantum computing? This is very much like the primitive programs for a GPU. You may do some type of matrix multiplication or something like that. We think there's 4 of them. I only showed 2 of them here. The first is the most simplest. I take a bunch of quantum circuits and I sample the output. And so you imagine, we just say it takes a list of instructions, give me the sampled output. The second is estimator, which says I take a problem, a parameterized problem, and I return an observable. So I basically send all the circuits and I do all that processing and return a single number. And so these 2 set going forward, but to go a little bit further and to sort of paint the whole picture, you've got this milliseconds of doing these loops through the Qiskit runtime. So that's one time that has emerged. You also have this new time that emerges, and I'll explain a little bit about that and try and then paint the whole picture of what is classical and quantum. We call this real time. This is time that happens within the quantum circuit. So I may measure some qubits, feed it forward, and predict them. And so it's definitely emerging that there are at least 2 time scales. Real time, so I can do things really fast. Near time, so I can get, with the Qiskit runtime, get efficiency out of it. And example of real time is quantum teleportation is the most famous. if you had the problem, many people would say swapping with a technology that has limited connectivity. So if I've got a superconducting grid, say versus, and that has a lot of connection, a lot of people claim that connectivity matters. It turns out by just adding the ability of doing a measurement and feed forward, the whole connectivity argument disappears. So you can do any Clifford operator in order constant time. You can do more other examples, obviously. Fourier transform is a famous one. But essentially what it is by bringing some classical computation within the coherence time of the qubit, increases the rate at which you can basically do more complex quantum circuits can be run with less gates, is the main message. So we call these dynamic circuits, and it's our goal to release them next year. The hardware is working, and these dynamic circuits will be bringing this ability for you to explore these new complex circuits this year. But now I wanted to go back to what I sort of set up with talking about classical and quantum. Do we have the time? Okay, I'll go fast through this section. So what does it mean to start to post-process the results better? So I call this error mitigation, circuit knitting, and enablement, and also eventually libraries. So what I think is the most exciting is when you start to get this architecture that can bring classical and quantum, you can start to look at problems like, I imagine I got a chemistry problem. Can I split it in terms of something that runs on a quantum computer and something that runs on the classical computer? And now I use the classical computer to call the quantum computer to change the different calculations that it does. You can say, well, I have a big quantum circuit. It's got some type of symmetry. Can I cut the symmetry in certain ways and glue the symmetry together and add these all together to calculate the answer to my problem? We call this entanglement forging. You can take this to the extreme, which we call circuit knitting, where we can cut in various different ways and then knit them all back together. These allow us to explore bigger circuits by adding classical computation. This allows us to explore a bigger problem by mixing classical and quantum. You can run, this one is, you could imagine you go in and you measure all the different types of errors that happen in your system. You can generate with probability, so it's not full error correction, so we call it probabilistic error cancellation, the errors that would happen, and we could sum them back up. And we already see that the without it compared to with it makes a huge difference. So this is a technique of bringing some classical computation where you imagine you basically generate a efficient model for your noise that you can resum to get your answer. You can compare what we call error mitigation between a method that runs classically and a method that runs quantum mechanically. And we already are seeing that the classical methods at scale perform worse than the quantum method. So this suggests that we're very close to seeing the point where we can do something with quantum that will be potentially more accurate than we can do with classical. And what this requires is you run various different circuits, add them together and extrapolate them to cancel the number that you want. But the essential point is by bringing quantum with I always say with a large C, classical, so this classical quantum architecture together, we can increase the accuracy with less qubits, and we increase the accuracy and we can reduce the number of qubits that we need to actually do relevant problems. And so what this means is, if by the innovation that we can bring in both of these, is it possible to make what we can do with quantum computing happen earlier than what it would take if I had to build a large enough system? And so can we solve these classical untractable problems sooner? And just to sort of summarize that, this is how I see it all sort of breaking down. You basically have to have libraries that simplify for the algorithm. You have what I called the Qiskit runtime, which I talked about. You need your quantum circuits that will run within it, and you need the pulse level calculations. You need all of this together to create an effective stack that allows you to do classical and quantum. And I'll skip the compiler for time. And what that means is you have your dynamic circuits, which we're putting out this year. You have your runtime, which focuses on performance. How do you get the most out of a GPU? You need a new architecture that can talk between classical and quantum. We are calling it quantum serverless, so it's event-based driven. And then ultimately, you would hopefully be able to easily run it. To show a video, here's an example of us getting this using IBM Code Engine, which is basically it's a program that allows you to, it manages the classical resources. So you imagine you have your code, you what this did, it sent it to the orchestrator, it started the actual writing of the parameters in the runtime. These parameters get read back out, so now then some calculation in the classical can be done here. It then can come back and repeat this loop many, many times, and in the end, the solution, I must have hit the button. The solution, by getting the progress, returns at the end for the user. And so you can see this all starting to get. We've made this MVP last year. And this basically, skipping going through it, it becomes a new architecture where I like to think of it as what the future of quantum computing will be, and I call it quantum-centric supercomputing. It will be a user, will just be declaring classical and quantum. I want to use GPUs. I want to use QPUs. It will have Qiskit runtime. It will be parallelized, so I can run many of these different workloads together. And you've got to think of how all this architecture works together. And just to finish, well, I'll show you the video of what we're prototyping. This is the IBM Quantum System 2. It's a new system beyond the System 1 that we're building at the moment. It's designed to be modular, so I can easily add components together. It's obviously, this is just a video and just a prototype, but you'll see as we go through it here, the system is in the middle, all the electronics are on the outside, and you can imagine a whole lot of these systems, because they're much bigger, there's 6 different doors, you can imagine many different processors inside it. You could imagine multiple of these processors all connecting together, and this is what we envision a future of quantum computing will look like. And on that, I'll stop and just summarize that, to me, it's these fundamental algorithms. It's about using dynamic circuits to do more. That's going to happen this year. The future is about combining classical and quantum. And we're already seeing clients and people in the community getting interesting. So I would say quantum computing is already here. Thanks.
네, 고맙습니다. Thanks, Dave.
No problem.
So we have time for some questions. If you have any, you can put.
Yep. Sorry? So I had it at the start. A longer talk I could go into how error correction works. Most people get confused and claim logical qubits, non-logical qubits. What really matters is, can I make a quantum circuit and keep showing that I can get it better and better? One way, obviously, to do that is I can encode the qubits. Everyone forgets about the, people make really rash, inaccurate claims, and they only count, say, the memory, how good is a 0 or 1. And usually if you're restricted to a surface code or a 2D lattice, the overhead is actually dominated by the T-gates and dominated by all the operations that are actually outside of that, and that limits more that goes into it. So if I look at error correction, and the way we do it at IBM internally is down 2 different paths. One is we ask the question, how do we mix error mitigation and error correction together so that we can run bigger computations? We put a recent paper out that showed we could replace the T-gates with error mitigation and keep encoding into the Cliffords. And then the other direction is, can we build hardware that supports low-density parity check codes? So can we build hardware that will support more exotic graphs? If you can do that, then you're not limited to the no-go theorems that restrict the number of sizes. So we go down the picture of that. But if you wanted how I see it as a capability, nothing more. As I go down the path to making larger and better quantum circuits, it is just a capability that extends the quantum circuits I can do. And the way I approach it is trying to understand how much of the circuits need to be error corrected versus error mitigated. And then the second is how much, what type of graphs will give you a much more efficient mapping. But I would recommend always ask, when someone talks about error correction, always ask, what are the gates? What is the encoding? And that will give you a much better answer than just, like, theoretically, the minimum code I can do is 5 qubits. That code is not a very good code to use.
We need to optimize for every circuit.
It could be that certain circuits don't need more. That would be why compilers and how we optimize compilers is a fantastic way. What I really like about the theoretical paper of putting error correction and error mitigation together was it said, well, imagine I error correct Cliffords, and theoretically error correcting Cliffords doesn't have much overhead. How good of circuits can I do when I post-process the results and just correct observables from my faulty T-gates? And it turned out that within, I forget what the number, but circuits of 10,000, you could make some claims that you were actually beating methods that efficiently simulate Clifford plus T-gates. And so then you can make some statements there. But to answer your real question, it comes down to what are the circuits, how do we correct those circuits, and then what amount of error correction you need on it. Now, I'm not going to be saying that I don't believe in error correction. We've always worked on error correction. It's a little bit more complicated than the doctrine that is, there's no, did I even use the word NISC? I refuse to use the word NISC. It's a little bit more complicated than the doctrine that people have set up that I have NISC computers and fault-tolerant computers. My view is I want to build larger and bigger quantum circuits, and I want to keep pushing them as fast as I can with higher quality and fidelity so I can push what can be done. And whatever tool I need to put in there, error mitigation, error correction, we will do it while we maximize what type of circuits we can do.
Okay. Any other questions?
Thanks for that. In the video of the Eagle chip, I wonder, there was a white ring around the chip, and I wonder what is that for? It's a cartoon rendition, but our qubits have a grounded plane. So ever since so it's a great question, and I really appreciate how much you've put into designing qubits. So ever since we put these in the box, this is actually a faulty line. It's not there. Otherwise, it wouldn't work. But the qubits are essentially inside a grounding box that is then coupled to a pad that goes to the different plane. But of course, I've dropped details from this. But I can tell that you've done a bit of designing of qubits.
Other questions? Is there a question in the Zoom window or YouTube? No.
Yep.
Hello, thanks for your nice stuff. I am personally an ISR rebellion, but I really appreciate your contribution from really providing a lot of the quantum computer. And I wonder, if you provide a lot of quantum computers for me for 5, 6, 7 years, so I think IBM has a lot of experience about something to
What we've learned by the users of our machines? Is that what you mean?
Like before, you already a lot of the researchers, and provide service.
So I skipped this because of time, but I really like this as an example. So imagine you wanted to do trotterization or some type of problem. Generally, the way we think of a compiler is we map it and then we actually compile out into the pulses. You lose context of what is happening. So what people have actually worked out is if this came from some context, if I can keep that context, that can help as I map it to my qubit hardware and get you to get much more efficient. So what I see the most rewarding from what people are doing is all the different ways they're actually taking what they're trying to compile and creating a much more efficient circuit that can run either through techniques that take what they were trying to do or even techniques that look for better ways of handling the noise. I've seen a lot of actual students and a lot of people developing different types of compilers. Did that answer the question?
Okay, so I think time is almost up. So let's back to the speaker again.
Thanks.
Thanks, Jay. 자, 사진 시간입니다. 포토 타임. 또 학생들 중에 그 제이 감백하고 백한희 박사하고 사진 찍은 사람 나오세요. 여기 사진 한번 찍고 가시죠. 한이. Yeah, good enough. Come over.
Yes.
Good enough. Yeah.
Is it okay?
Yeah. 불 켜주시고요. 학생들 나오세요. 좀 뭐 사진 하나 찍고. 임 박사 불 좀 켜줄래요? 문 밖에 여기. 예.